Okay, great. We will continue on today in chapter 7, and we are talking about sampling distributions. So we left off on Monday talking about sampling distributions, and we said a sampling distribution is the distribution of all possible values of a sample statistic That's weird. Okay. So sampling distribution is the distribution of all possible values of a sample statistic, okay, such as p hat or x bar for random samples of a given size drawn from the population. And to illustrate this, we said, imagine we had a tub of candies, so our illustration was, we said, imagine we had a tub of Reese's Pieces candies, and that in the population proportion of orange pieces was 0.3. And we said, let's imagine repeatedly drawing random samples of a given size. I think we said 50. Let's imagine repeatedly drawing random samples of a given size. And for every random sample we draw, we're going to calculate the p hat that we see. And we're going to do this thousands of times, keeping track of every single p hat we see. And that will build up kind of the sampling distribution that we're interested in. So we repeatedly take random samples of a given size. So we'll say 50. Okay. And for each random sample, we calculate p hat. Okay. And we keep track of all the p hats. Okay. Did I turn down the lights? Yeah, I don't know how to do that actually. I can do this, but then it keeps getting darker for the front row. Can you guys still see your notes? We're okay? All right. So we keep track of all the p hats that we see, and then and that's pretty much our sampling distribution. So of course, because of random chance, we would expect the different p hats we see to be centered at the population proportion of 0.3. Okay, so but not necessarily equal to it. So because of random chance, p hat can be larger or smaller than 0.3. But in the long run, we expect them to be centered. Centered around the population proportion P. Okay, in this case, population proportion P equal to 0.3. Right? When we created the sampling distribution, we had 0.3 somewhere around here, and then we had other values that were kind of like this. This is just and the idea was, this was the sampling distribution that we got, but it sure looked like the normal distribution. Okay, so we said the sampling distribution something is happening. Okay. The sampling distribution looks like the normal distribution. All right, so I'm hoping this looks familiar. We're kind of reminded of what we did on Monday. All right, and so, as far as this class goes, we're going to say, it looks like the normal distribution, so we'll call it the normal distribution, okay? Or we're going to say we can approximate it using the normal distribution. In perhaps a more mathematically rigorous class, you would have to prove this result, and and rather than just saying, it looks normal, and so you might have to jump through some hoops there. As far as this class goes, we're not going to bother. I'm not going to try to prove that indeed the normal distribution is a good representation of this. I'm just going to say it is, and you're going to take me at my word here. So let me, can I flip to the next page here? Yeah? Okay, I'm glad I have your approval. So this is something called the central limit theorem. And it's kind of a big deal. The central limit theorem, and I'm going to give you just a paraphrased version, okay? Because the real version is more formal and math speak. So the paraphrased version is that the sampling distribution of p hat and x bar can be approximated with a normal distribution. As long as certain conditions are met. And specifically for p hat, for the sampling distribution of p hat, we can approximate it with the normal distribution. With mean equal to p and standard deviation equal to the square root of p times 1 minus p divided by n. Okay, so we're just gonna say this, and you will accept this as true. Okay. Whereas, you know, if you decide to major in statistics, or if you decide to take some upper division statistics classes, you know, one of the classes that you might take is called Stats 100B. And you will prove this result, okay? You would prove this result. But that's beyond the scope of our course. We're just going to say it works, and that's what we say. Okay, so let me just kind of give you an example. Well, this part, the mean equal to p, I think this is intuitive. And we just talked about it on the previous slide. We said if the population is 30% orange pieces of candy, whenever I take a random sample, sure, I could get 32% orange, or 34% orange, or 26% orange. But in the long run, we expect overall these different values of p hat to be centered around 30%, the value p, okay? Or whatever proportion we're talking about. Let's say, you know, in the world, let's say 51% of people are female. Let's just, you know, it's something around there, okay? Let's just say 51% of people are female, and so whenever we take a random sample of people and we ask, are you female? And in the long run, we would expect around 51%. You know, the samples will vary. Some will have more, some will have fewer, but in the long run, the average will be something around 0.51. Okay, that's what we might guess. Okay. So you know, that's what we have. The standard deviation, this is a little bit less intuitive. I'm not going to try to derive or explain where this is coming from. We're just going to say this is the standard deviation here. Let's do a little example here. Okay. So the example we've been using was that, you know, in the population, we'll say 30% of the candies are orange. Okay. And then we'll say we draw random samples of size 50. And so we can ask, what is the distribution that can approximate our sampling distribution? Okay, what is the distribution that approximates the sampling distribution of p hat? Okay. And so our answer is using the central limit theorem. Okay, so from the central limit theorem, okay, we can approximate with the normal distribution. Okay. What is going to be the mean of this normal distribution? The mean is equal to p, which is equal to 0.3. And the standard deviation of this normal distribution is going to be equal to what? The square root of p times 1 minus p divided by n, which is the square root of 0.3 times 1 minus 0.3 divided by 50, And so this gives me 0.3 times 0.7 divided by 50. I get a standard deviation of 0.06481. So based on the properties of the population, we're saying if the population is 30% orange and we draw random samples of size 50, we can ask, what is the distribution that approximates the sampling distribution p hat? We will say that's the normal distribution. It has this mean, the mean equal to p, and the standard deviation is equal to this. Yes, question?
Is this the same as a standard error?
Yes, this standard deviation of the sampling distribution, that is the standard error. I guess I can, I can put that. So this term, the standard deviation, this is also known as the standard error. Okay, and maybe I'll define the standard error maybe in a slide or two here. Okay. Is this okay? And so we can use this to then answer questions about random samples. All right, and so this is where things start building. And so so I'll give you a clicker question here on the next slide. Okay, and so again, we'll start off with the same. We'll say the population is 30% orange pieces. We take a random sample of 50 pieces of candy. Okay, and the question is, what is the probability that a random sample will have a p hat that is greater than 0.4? Okay, and so let me put up some answer choices here. So okay, so go ahead and try this out. If you need to consult with your neighbor, you can consult with your neighbor. And if you're watching online, I'm going to pause the video here. And when I unpause, we'll go over the answer. Okay, let's take a look at how you guys responded. Oh, wow. Okay, everybody, pretty much everyone got it right. So that's great. Now I feel like, well, do we need to do this? All right, so the idea is, you know, in the population, so we know that 30% is orange, so when we take a random sample, we know that p hat comes from a normal distribution, and the mean is going to equal 0.3, meaning that when we draw a random sample, sure, our random sample could be higher than 30% or lower than 30%, but overall we expect it to be centered at 30%. Okay, so we did this on the previous slide, and we said on the previous slide we also said the standard deviation, or the standard error, is going to be 0.3 times 1 minus 0.3 divided by 50, and when we computed this out we got the value 0.06481. Okay, so this is the first step. The first step, step 1, is figure out the normal distribution. Okay, and then step 2 is work through the problem as if it were a normal distribution problem. So I'm going to just call this work through the normal distribution problem. Okay. And so once we have our distribution set up, well, we say, okay, with a normal distribution problem, I've got this value 0.3. I'm drawing a cut line at 0.4, right? We want, what's the approximate probability that a random sample will have a p-hat that is greater than 0.4. So I draw a cut at 0.4, and I want to know, okay, what is this probability that we get? All right, and so my z is going to be 0.4 minus the mean of 0.3, and I divide by my standard deviation of 0.06481. When I do this, I get a z-score of 1.54. I look up 1.54 in my table. The area to the left of 1.54 is 0.9382. That is this side. This side is 0.9382. Therefore, the area that I want is going to be 1 minus 0.9382. So the area to the right of 0.4, which is what I want, area to the right of p-hat equal to 0.4 is 0.1 minus 0.9382, which equals 0.0618. And that's our answer. Okay. So, for this problem, I gave you a little bit of a hand by calculating the normal distribution for you on the previous slide. On an exam or something, I might just give you the statement of the problem, very similar to this, but I won't tell you what the mean and standard deviation is, and you'd have to figure that out yourself. Okay, but I think that's a reasonable thing.
What information would you give us for us to find out the z?
I would tell you that the population has this proportion, and you're taking random samples of this size, and then I'll say, what's the probability that your random sample is this percentage or lower, or this proportion or higher, or something of that nature. Okay. There was a little, when we talked about the central limit theorem, we said the sampling distribution of p-hat and x-bar can be approximated with a normal distribution as long as certain conditions are met. Okay, so let me talk about those conditions that must be met for us to use the central limit theorem. Okay, so in order for us to use the central limit theorem, certain conditions must be met. Okay, because if these conditions are not met, then our sampling distribution will not resemble the normal distribution. So, did you guys start your sampling distribution lab yesterday? No? Oh, tomorrow. I'm sorry. Yeah, yesterday you had the quiz. I apologize. Yeah. So tomorrow you're going to start your sampling distribution lab, and And the first, when you start it off, you're going to create your sampling distribution, and it's not going to look like the normal distribution. It's going to look like lines, right? So certain conditions must be met, okay? If these conditions are not met, then the normal distribution does a bad job, or I'll say the normal distribution cannot be used to approximate the sampling distribution. Yeah, it's kind of funny. The lab that you're going to work on tomorrow, you can tell it's a dated lab because you're dealing with a proportion, and it says what percentage of teens text on a daily basis, and the number that they're using is, we're going to say, let's say in the population 20% of teens text on a daily basis, and I think it's fair to say that the proportion is higher today. So anyway, this is that's what you're going to use. Okay, so anyway, if these conditions are not met, the normal distribution cannot be used to approximate the sampling distribution, and therefore we can't answer questions like the one we just asked, because the one we just asked depends on using the normal distribution, and we don't have a straightforward way to answer those questions. Okay, so anyway, these three conditions, there are three conditions. Okay, number one, we call this the random and independent condition. Okay, the random and independent condition means that the sample that we are looking at has to be selected randomly, and the members in the sample have to be independent of each other. Okay, so the sample we are looking at must be selected randomly. And the individuals must be independent. So that is the random and independent condition. The second condition is known as the large sample condition. Okay. The large sample condition basically means the sample must be large enough. Alright, so how do we know if a sample is large enough? For when we're dealing with proportions, for proportions, we must have at least 10 successes and at least 10 failures. Okay, and so this means your sample size has to be at least 20. That's the fewest number of smallest sample you can possibly have, and that's with having exactly 10 successes and 10 failures. 10 who say yes and 10 who say no. But in general, you're going to need a larger sample than that, and especially if you're dealing with something that's pretty rare, like some kind of genetic disease or something. Okay, you might survey 300 people, but after surveying 300 people, you might find that only 2 people have this genetic condition. Okay, your sample is not large enough to use the central limit theorem. You need to survey you're going to have to survey like 5 times that, 1,500 people or something like that, so until you get at least 10 yeses, okay? Or if, on the other hand, if you're surveying something and every it's really common, and 99% of people are saying yes, you need to have a survey so you have at least 10 failures. You need at least 10 successes and at least 10 failures. Okay? If counts are not given, you have to figure out the counts yourself. You have to figure out the counts, and so you would just do n times p and n times 1 minus p. Both have to be greater than 10 for the large sample condition to be met. So you need to have at least 10 successes and 10 failures. And if you're not given counts, you have to figure out the counts by doing n times p for your number of successes, and n times 1 minus p for your number of failures. Both of those numbers have to be greater than 10. All right, and the last number, or last condition, is the big population condition. The big population condition says that the population must be big compared to your sample. Okay, so the population, and in general we say the population must be at least 10 times bigger than the sample. Okay, unless you are sampling with replacement. The idea here is that, you can imagine a deck of cards. In a deck of cards, there's 26 red cards, 26 black cards. Okay? So the first time you draw a card out of the deck, you have a 50% chance of drawing a black card, right? You got 26 red, 26 black cards, you got a 50% chance of getting a black card. Let's say you draw a card and that card is black. Then what remains in the deck is you have 26 red cards and 25 black cards. Okay? So technically your second card that you draw is not exactly 50% chance of getting black. It's a little bit different. Okay? What we're saying is that as long as you're drawing less than 10% of your sample, as long as you're drawing less than 1/10 of your sample, the amount that it changes doesn't really affect it too much, that we don't have to worry about it. Okay? But you can imagine, after drawing 10 cards out of the deck, what you have in your sample will affect what's remaining in the deck. And so we're saying if you draw too big of a sample, or if your population is not 10 times bigger than your sample, then that could be a problem. Okay, and the exception is that if you sample with replacement, then you don't have to worry about it. You can take really big samples. So with replacement means, I start off with 26 red cards, 26 black cards. I draw out a card, it's black. Then I put it back in the deck, so I still have 26 red and 26 black. And therefore, the next card I draw, I still have a 50% chance of getting red and a 50% chance of getting black. And it doesn't affect it. And so I can keep drawing and replacing, and I don't have to worry about these things changing. But if you're sampling without replacement, which is most of the time you're sampling without replacement, you cannot get, your population needs to be at least 10 times bigger than your sample. All right, is this okay? So I'm going to give you an example here, and this is your second clicker question, and you're going to have to decide which condition is violated, or maybe none of the conditions are violated. Okay. All right, and so the conditions, all right, and the question is, which is violated? All right, and so your answer choices A, B, C, D, A is random and independent. You don't have to write this down. And I'll type up the question on in Word here, just because it'll be faster. Okay, random and independent, large sample, big population, and then we'll say no conditions violated is option C. Did Microsoft Word not start? Oh, here it is. Oh, of course. All right, so let's say, okay, so let's say you want to conduct, can you guys read that? Conduct a survey of UCLA students. All right, so what do? All right, so you decide to stand on Bruin Walk and ask questions. Excuse me, can I ask you a question? All right, and okay, and you survey 200 people who walk by. We'll say 25 people. 25 of those people answer yes to whatever question you had. Okay. Let's just say to your question. And the question is, can we use the central limit theorem to approximate our sampling distribution? Okay, so I will take this and put this right here. Okay, now you can talk to your neighbor about whether you think the conditions are met, or if any of these conditions are violated. What do we have? Okay, let's take a look at how you guys responded. And the correct answer is A, random and independent condition. Okay. All right, let's go over this. Let's go over this. All right, which condition is violated? Okay, so let's take a look. Random and independent. The problem here is you are standing on Bruin Walk and asking questions, and you survey people who walk by. All right, that is not random. Okay, surveying people who walk by on Bruin Walk will not be random. Okay, this is known as convenience sample. Okay, and basically this means you're only going to get people who walk on Bruin Walk. All right, so again, what's the population that we're interested in is UCLA students, right? This is kind of the population that we're going after. And not every UCLA student goes on Bruin Walk. Now, a lot of them do, but depending on the time of day you're on Bruin Walk, you might get more people who have morning classes, or people who have afternoon classes, people or the day of the week, people who are Tuesday, Thursday, or people who are Monday, Wednesday, Friday. You're going to get people who go outside and walk, okay? And that's not necessarily everyone. That's not, depending on what's going on, some people may be less inclined to be walking around on Bruin Walk, okay? And then, how many people even will engage you on Brew and Walk 2, right? Okay, so serving people who walk by will not be random. That's a convenience sample. You know, just other samples that are not random. So yeah, any type of where you just kind of stand somewhere, like you stand at the corner of the street and you ask people, that's not going to work, right? Internet surveys, those will never be random, okay? Because the internet, well, survey responses on the internet can seriously be manipulated as well. And it's only going to be people who visit whatever website you're talking about. I don't know if there's a website that everybody uses, right? In the US, probably the number one, I would imagine, would be Google, okay? But not, you know, you're not going to get Microsoft employees there, right? I mean, you will, but not as many. So, you know, internet surveys, not going to work. Even if you get a random sample, if you don't get 100% response rate, okay? So even random samples or random surveys that do not have 100% response. Okay? These will not be random. This is what we call non-response bias. Because, you know, you might be asked for a survey. You're using an app, and it says, how do you like this app? And then you just, what do? You just click X, right? You just say, I'm not going to leave you a rating, right? So, unless you're, like, super passionate about the app or you're, like, super angry about the app, okay? So, unless you have 100% response rate, that's not going to be random. Okay, let's take a look at the other conditions. Okay, large sample condition, this is met, okay? Okay, the number of successes, we have the number of yeses, we have 25, which mean the non-yeses, I don't know if that means a non-yes, or maybe that means a no, or I don't know, maybe there was a maybe option or whatever. A non-yes will be 200 minus 25, we have 175, okay? These are both are greater than 10, so we're good there. Big population. The population of interest is UCLA, right? UCLA students. Okay, and our sample was 200, so n is equal to 200. So if we do 200 times 10, that is equal to 2,000. Are there more than 2,000 students at UCLA? Yes, so population is bigger than 2,000. So the big population condition is met, okay? So condition is met. Okay, we'll end here, and we'll see you guys on Friday.